In this video, we will look at an example of how we can linearize a nonlinear process model. And to give you an example, I will take the case study of the inverted pendulum on a cart. The description of the inverted pendulum of the cart is available in the previous videos. So if you haven't seen the description of the inverted pendulum video, please look at that video before proceeding this video. In this video, I will give you a detailed example of how we can linearize a nonlinear process model. Now, let us recall the inverted pendulum on a cart. The inverted pendulum on a cart is shown in a very simplified diagram here. The mathematical model of this inverted pendulum on a cart is described by 4 states. The first state is the alpha, which is the angle between the pendulum and the vertical axis, which is denoted by y-axis. Omega is the angular velocity of the pendulum. x2 is the position of the cart on the horizontal surface. And v2 is the velocity of the cart. The model of this inverted pendulum is a nonlinear model, as you can see it here in these 4 equations. This is a collection of ordinary differential equations. Now we have to linearize this nonlinear model of this process so that we obtain a linear model. Here the states are alpha, omega, x2, and v2. The equation describing the dynamics of the first state is this one. We will write this equation as function number 1, and function number 1 is simply omega here. The second nonlinear equation is here, and we can simply say that this is f2, and f2 describes how angular velocity changes with time. Similarly, let us consider that this is function number 3, and this is the last function denoted by f4. The parameters of the system are as given here. The mass m1 is 1 kilogram, m2 is 2 kilograms, the length of the pendulum is 1 meter, and kt, which is the friction factor, is 0.1 kilograms per radian squared. Okay, now we will linearize these 4 nonlinear equations so that we get the equation of this form, where x is a vector containing the states. In the previous video, we have discussed on details of how we can obtain linear model. Here, we will simply apply it. Please look at the previous video on details about how Taylor series approximations have been done to linearize a model. Here we will directly find out the system matrices AC, BC, and CC. We know that AC is denoted with the Jacobian matrix in such a way that we take the partial derivative of each of the functions with respect to each of the states. And all of these partial derivatives have to be evaluated at the operating point. In our case, the operating point is. So now let us first define the operating points. We will linearize the system in a way that the pendulum is inverted and the cart is at the x2 equals to 0 position. So when the pendulum is inverted, then alpha will be 0 because this pendulum will be here. x2 will be 0. When the pendulum is perfectly inverted, the velocity of this pendulum will also be 0 because it's stationary here, it's standing upright. Similarly, the velocity of the cart will also be 0. So we will linearize our system in a way that our operating point are 0 radian, 0 angular velocity of the pendulum, cart at the origin or when x2 equals to 0, and similarly the cart is not moving, so velocity of the cart is 0. So we linearize with respect to this operating point. Now before we do this, one thing I would like to express here is that for very small angle when alpha equals to 0, because we are linearizing around alpha equals to 0, we know that sine of alpha will be nearly equals to alpha, and cos of alpha will be nearly equals to 1. For example, if we put cos alpha and alpha equals to 0, then cos 0 is 1 as we know. And for very small angles alpha, around 0, sin alpha is simply the same angle, discarding the sinus function. Since we are linearizing around alpha equals to 0, we can make use of this trigonometric relationship and we can simplify our model. So when we do that, these four equations will be changed. Let us write those four equations. Let us first take the f1 function, our first equation. This will remain as it is because here there is no place where we can utilize this property. So it remains as it is. However, if you look into the second ordinary differential equations, here we can replace cosine to alpha with 1, and here we can replace sine alpha with simply alpha, and so on in the other places where there are cosine and sine. Now, if you compare this function with this function, the thing that is different here is that instead of cosine alpha, we just wrote it 1 here instead of sine alpha. Here we simply wrote alpha here, and so on in other places. Let us simplify it further. Now, let us also try to change these equations, but here since there is no place where we can utilize this expression, so it becomes as it is. And finally, let us also try to modify this one for small angles. Here we can replace with 1, and here we can replace by alpha. Let's do so. Please also note that this d omega by dt is this whole expression, so this in fact is f2. Now we have all our functions f1, f2, f3, and f4 for small angles alpha equals to 0. Now we can utilize this matrix, or we can calculate this matrix using the simplified functions or ordinary differential equations. Let us do so. Let us first calculate for alpha, which is the first term of A. Will be 0 because there is no alpha, so this is considered to be constant. Remember that this is partial derivative taken with respect to alpha. Let's move on to the second element of AC, which is finding the partial derivative of the first function with respect to omega, and this will be 1. Similarly, the partial derivative of the first function with respect to the third state, which is x2, will be 0, because there is no x2 term, and this is considered to be constant, and derivative of constant is 0. Partial derivative of the first function, which is this one with respect to the last state, which is v2, is also 0 because here is no v2 term, and omega becomes constant, and derivative of constant is 0. So now we have filled up the first row of AC. Now let's take the second function, which here in this case is this function. So we have to now find the partial derivative of this function with respect to all the states. Let me show you an example for the first two states, and for the remaining it follows easily. I have rewritten the equation. Now let's find the partial derivative with respect to alpha. So we have to see the places where there is alpha. So this term is constant, so that will be 0. Then we move to the second term here is alpha. So we will have. Here we also have alpha term, so we will be having. Thus finally we have the following expression. Now is the important thing. We should remember that we should evaluate this function at operating points. W2 op is 0, in fact all of them are 0. So if you put W to be 0, then this term will be 0. Thus finally we get. Okay, now similarly we will also have to find out the partial derivative of the second function f2 with respect to the remaining three states. Let me show you one more example with respect to omega. Here is the omega term, so we should take this into account, so this will be omega square. So if we take derivative of omega square with respect to omega, then that will be 2 omega. So we have this term doesn't have omega, so it will be 0 now. Let's move on to this term. Here we have omega, which is in square, so we will have. And this we will evaluate at operating points, which are all zeros. So omega will be 0. Here also we have to put omega to be 0. Thus the whole term becomes 0. Therefore partial derivative of f2 with respect to omega is simply 0. Similarly, if you evaluate with respect to x2, then you will get 0. And del f2 with respect to v2 will also be 0. Because in this equations there is no x2 and v2. So all of this term is constant, and derivative of constant will be 0. Okay, now we have finished with the second equations. Let's move on to the third equation. This is the third ODE, and this is f3, and we have to take partial derivative with respect to f3. With respect to alpha is 0, there is no alpha term here. Because here is v2 and del v2 by del v2 will be 1. This was pretty easy and straightforward. Finally, the fourth ODE. Let me rewrite the ODE first. Now, let us try to find the partial derivatives. Here is the alpha term. So taking only these two, first we will get, this will be 1. Here there is no alpha term, so this will be 0. And here this is constant, and this dw by dt is the whole equations that we used it before. Here there are alpha terms. Okay, so that simply becomes as follows. Here this dw by dt is f2, so instead of dw by dt, we can write del of f2 over del of x. And this term we have already evaluated before, let's see it. Del of f2 with respect to alpha is here. So we can directly write this here. This comes from the top here. Let's also calculate with respect to omega. Here is the omega term, and here is the omega term, but as we know that this will be omega square. If you take the partial derivative, and if you evaluate twice of omega, then it will be 0. Let's see for this term. Evaluate this at the operating point. An operating point of omega is 0, so this whole point will be 0 at omega OP. Similarly for this term, we can write, and this we have already evaluated. Del f2 del omega is 0. So this is also 0. Therefore, similarly we will get, because in this term there are no v2 and there is no x2 term, so it will be 0. Thus, we have calculated all of the necessary partial derivatives for calculating AC. I will go on filling it up. Now let's fill up this part which we have calculated, and the remaining part which we have calculated already. Let's fill it up. This matrix. This is AC. Similarly, we can also calculate the partial derivative with respect to u to find out BC. And for our case, u is the control input, and that control input is f. We'll be having single column because we have just one control input, and that is simply f. Well, this was f2 actually. So del of f2 with respect to del of f will become, we only take into consideration this part, so that will become -1 by m2l for f1. We know f1 is d alpha by dt, and it's simply omega, therefore del of f1 with respect to f is simply 0. Let's go to f3, and f3 we have. And finally the last function f4. Now we have calculated all of the necessary elements of BC. Then finally, BC will be 0, which is this part. Okay, then finally we also have to write the linear measurement equation. So let me recall it here. Now, let's assume that we can measure alpha, and we can measure the position of the cart. And let's assume that omega is not measured and v2 is not measured. So our measurement equation consists of only alpha, and x2 and alpha, and x2 are these two components of x, so our delta y in deviation form will be cc of del of x, where we will take into account alpha, because this is measurable. Omega is not measured, x2 is measured, so we will have 1 here. v2 is not measured, so we'll have 0 here. Thus, cc is very easy to define for this example. Thus, we have now our linear model in deviation form. And here's something that I would like to explain. When you linearize a nonlinear model about an operating point, you will always get a linear model in deviation form. And remember, the deviation form is how much is the state at the current time away from the operating point. In this case, since it is all zeros, we have a special form. Or this can be written in a simple form, which the students know about it very well. So if you put xop to be 0, then simply delta x will be x. So instead of delta x, we can simply write x. But if your deviation variables are not all zeros, then please remember that you should subtract the operating point to find delta x. And similarly, if you want to find the actual x, then you have to add the operating point to delta x. Most of the students forget either to subtract or to add this operating point. And if they are not zeros, then forgetting to add non-zero numbers will give you wrong simulations and wrong results. So please take care about the operating point.